So just in case, probably everyone remembers that tomorrow we have no class. So today and Wednesday will be the last 2 days where I cover material for the midterm that we have next week. And it will be kind of like the same stuff, like same format, and I'll send you the practice exams and all that stuff probably around Wednesday or Thursday morning. So I don't know if there are any questions before I begin. There are basically two topics left that I wanted to include on this exam. So the first one is called the mean value theorem. It's kind of like an interesting theorem. It has like many useful applications. I mean, like, for many of these theorems and calculus, going through the proof would be it's kind of useful, but at the same time, it's not the focus of what we're trying to do. We're trying to learn more like how to use it. Especially if you like what the theorem says is relatively intuitive. But yeah, if you were interested in like going through the proofs of these theorems, I think that the book sometimes gives an idea of why they're true, and also like they're more like advanced courses if you're majoring in math or whatever, where you can actually go through all the details of why everything like this works. But for us, it would be more like kind of like just knowing how to use it, um, instead of like trying to go through all the details of why they work. So we're going to have in the mean value theorem, we're going to have a function of one variable. Okay, yeah, I'll put it like this. So f of x is going to be a function that is continuous on an interval. So let's say the interval is AB. That's usually the name for interval. So it's going to be continuous on this interval. And you also have to assume that and has a derivative on the for any value of x in that interval, there is a derivative. Okay, so if you again like notice what the hypotheses are saying is that the function is continuous with an inequality that is less or equal, greater or equal. So here is like less or equal inequalities, and here for the derivative, like the only thing that you need is like for the derivative to exist for the strict inequality. So meaning this is like a closed interval, and this would correspond to an open interval. In practice, like those differences, like those subtleties, like don't play a bigger role. So it's like important, like usually for like the applications we will have in mind, like the derivative, will also exist at the endpoints. But I'm just saying, like, it's really that is not that necessary. But yeah, at least it has a derivative at any point on the open interval a b. Okay, and then but let's do like a picture, because again, like a picture kind of will clarify what the mean value theorem says. So if you look at the point A, you get A comma f of A. And if you look at the point B on the graph, you will get the point B comma f of B, right? So there is like a line that connects these 2 points. So this is a line connecting P and Q. Let's call these 2 points P and Q to okay. And so this line has a certain slope, right? That slope is very easy to find because you have the 2 points. So okay, and then what the mean, so you have this line, and what the mean value theorem says is that there is at least some point between A and B whose tangent line has that same slope. So let me draw this first. Maybe it will be this point, PQR, let's call it R. So what the mean value theorem says mean value theorem, which is sometimes called MVT, by the way, says is that there exists at least a point, at least one point give me a second, please. There's at least one point C between A and B. With the property that the slope of this, the tangent line to the curve, remember the slope of the tangent line is f prime of C. So this the mean value theorem says that there's like a point between A and B whose tangent line has the same slope as the slope that connects the endpoints of the line that connects the endpoints. Okay, so let me give you a chance to copy this first. So meaning another way to say it is that these two lines are parallel, right? So because that's another way to say that the slopes are the same. So the tangent line to the points, let's call this point R. Oh yeah, I already called it R. To the curve passing through R is parallel to the line connecting P and Q. Is that making sense? Like, let me stop here. I don't know how clear this is so far. So is it? I mean, if you do a picture, it's kind of in like it looks reasonable. At least from the picture that I am drawing. Of course, like it does require like a proof, but you know, it would take us too far to actually prove it. But like, you know, it kind of makes sense. Okay, so I should let me see if okay, let me do it in a couple like the thing with this theorem is kind of similar to the squeeze theorem or the intermediate value theorem, if you remember those. The problems can be a bit tricky. So we do have to go slowly on the different examples that they that you can run into doing this. So there's like a physical, but first, before doing some examples, let's give like a physical interpretation of the mean value theorem. So here's a physical interpretation. Imagine that you have a road. You have a road and you have a car, and you're driving along this road. Okay, well, it's kind of an antiquated car. I don't know how to draw a Tesla, so um, so driving along a road on a road. Okay, so when you're driving, like if you think of the road like being aligned with the x-axis, right? So here's the x-axis or the number line. You can think of the position of the car, let's say, as a function of time, right? So you can think of the position. That's what like in physics you would also usually call x of t. So position of a car of the car at time t. Is that making sense? So maybe you have like here, oops, like I should probably write it this way. So x of A would be the position of the car at time A. Oh, well, let's call it T1 and T2 because that's like, that would look a little bit better. Okay. So what physicists usually do, and you probably may have seen this before, is that they'll show you a graph of x as a function of time, right? Which can be a little bit confusing, just because like usually in these representations, x is like the vertical axis. But again, the point is that here you have like maybe that's how the position as a function of time looks like. Let me try. Let me draw it a little bit more curved. Okay, maybe that's like how the position of, as a function of time looks like. So maybe at time t1, let's say t1 is time here. Here's like, let me move it a little bit to the left. Maybe at time t1, this is like the position of the car. And then time t2, this is the position of the car, like here. Okay. So there is this line connecting, right? This is kind of like our P and Q from before, right? So this is P and this is Q. So there's this line connecting these 2 points. What's the slope of this line? It would be x of t2 minus x of t1, right? Because those are the vertical values, the y, it's kind of like the y values in this case, divided by t2 minus t1. Is that making sense? Why the slope is this quantity? And what that is what people call the average velocity of the car, because on this interval, because this is final position. Oops. If you think about like as this as like the initial time and final time, this would be final position minus initial position divided by the time difference, right? And that's precisely how you would define the average velocity. Okay, so what the mean value theorem says is that there's going to be a point, let's call it T3. So instead of calling them A, B, C, I'm calling them now T1, T2, T3. What the mean value theorem says is that there are going to be a point T3 or T star if you prefer. So that, let's call it T star. There's going to be a point T star. So by the mean value theorem, there is a point, there's a time, like, because now the point is time, there is a time T star I'm trying to find the color that I used here. Ah, here it is. The star where the derivative, right? X prime of t, X prime of t star equals this slope, so equals the average velocity. But I mean, I think I may have mentioned this once when we talked about this briefly, but what's the derivative of position with respect to time? What's the interpretation of that? This is also like what you would call the xdt, right? This derivative, the xdt. So what would that give you? Okay, then actually the velocity, like the instantaneous velocity. So what the mean value theorem says is that there's at least one time where your instantaneous velocity equals the average velocity on a given interval. So in other words, mean value theorem means there is at least one time where your instantaneous velocity equals the average velocity. Is that making sense? Are there any questions about this? Okay, so let's start with the mm, okay, yeah. Okay, let's start with a problem for you to think of, which is related to this physical interpretation. And this is sort of like the type of problem in the mean value theorem. So like it will give you like a good idea of the flavor of those theorems. So let's start with a problem for you to think, and then we'll discuss it together. Here's a problem. So the velocity of and this is like a practical problem, it's one that in real life you could be curious about, like, it's not completely artificial. It's like you could imagine someone being interested in knowing this. So the velocity of a train is kept between 40 miles per hour and 50 miles per hour during a trip of 200 miles. What can you say about the duration of the trip? So this is asking, for example, so you know the train's traveling between 40 miles and 50 miles per hour, right? On a 200-mile journey. Um, does that mean, could that have happened in 30 minutes or 1 hour or 2 hours or between 5 and 7 hours or between 1 and 3 hours? So it's asking you to give like some sort of estimate of how long the train trip, like the trip could have lasted. Okay. And again, it's kind of like a question that, like, it's like a reasonable thing you could have be curious about. Uh, like if we're doing it right now, it's because it's related to the mean value theorem. So let me give you like at least 5 minutes to think about it. And then we'll discuss how to, but try to see how can you use a mean value theorem statement to give you like this estimate. So yeah, but it's fun to think about it first, and then we'll discuss it. So let me give you like, yeah, let's say 5 minutes, and if you want also to grab something, water or do something else, you can take this as a mini break. Okay, so what's your estimate? How anyone came up with a guess of between how many hours the trip could last? Yeah, right. So here's like a intuitive way to think about it. Imagine you were always traveling at 50 miles per hour, right? Like the train had like a constant velocity of 50 miles per hour, and it's like a 200-mile journey. So that should take 4 hours, right? Because 50 times 4 is 200. Is that making sense? And if the train, on the other hand, had, um, let me write it down. So here's like an intuitive idea. So here's like the intuition behind it. If train traveled at always at 50 miles per hour, it would take 4 hours, right? And if the train traveled at 40 miles per hour, it would take 5 hours. Is that making sense? So the thing is like in practice, what's happening is that it is not necessarily traveling at 40 all the time or 50 all the time, right? It's kind of fluctuating between those two. So what you would expect is like for the time that it takes you to be between like those two extremes, between 4 and 5 hours, right? And kind of like the mean value theorem, what it does is kind of justify that idea. So in the proof of the mean value theorem, what you can do is like, again, you have here like the time axis, you have here the x-axis, like you don't know what the train is doing, like let's put it like this, maybe. This is like the position of the train at as a function of time. And in fact, I could try to even copy paste like this. Oops, let me see if I can paste this picture. So what we know is that by the mean value theorem, x prime at t star, right, is x of t2 minus x of t1 divided by t2 minus t1, okay? But x of t2 minus x of t1, that's just, you know, how much distance has been traveled by the train. So that's why you end up getting that x of t2, oops, you should having x prime. So x prime of t star equals what? 200 miles divided by t2 minus t1. Is that making sense? Why I replace the numerator with 200? Because the numerator is just a change in position, and the change in position corresponds to the distance traveled by the train. And then you just use the velocity, and here this is like the velocity, but the velocity is being kept between 40 and 50 miles per hour, right? So that means that 200 miles over t2 minus t1 is between 40 and 50 miles per hour, or 50 miles per hour. And from there you get that the t2 minus t1 is between 4 and 5. Like you can divide by you can divide it all sides, like you can cancel the miles on every side of the inequality, and you divide by 200 every side of all the sides of the inequality, so you get 240 and over. And when but the thing is that here, like t2 minus t1 is in the denominator, so when you flip it, it reverses the inequality, so t2 minus t1 is between 4 hours and 5 hours. Is that making sense? Any questions about this question? Or this problem, this example? So here's another example in the spirit of the mean value theorem. Let me see which one I want to do first. Okay, let's do the following. This one is very cool, and it's like another interesting thing. So here's example 2. Okay. And this one should be like, it's like an inequality that maybe you never thought about. Um, this one is a lot less obvious, if less intuitive than the previous problem. Um, in fact, let's try to make a picture to see what this is saying. So what was the graph of cosine like? It was something like this. So I don't know. It's saying like, it's saying that if you take like x1 to be here, for example, so that's cosine of x1, and x2 to be here, for example. So here's cosine of x2, right? Then the difference in the y values, which is x2, cosine of x2 minus x1, would be less, or will be less than between this difference of x2 minus x1 and minus x2 minus x1. So kind of gives you like and which in this picture would not be that accurate then, like, but it's kind of telling you how big the cosines can differ in terms of its arguments, right? If you think about this as the angle, so it's giving you how much the cosines are, how big the difference in the cosine can be, in terms of the angle. But the proof is actually relatively straightforward once you have the mean value theorem. If you use the mean value theorem, what does the mean value theorem says? It says that you had this line which connects, those two endpoints, And there is a point on the graph right between x1 and x2. Let's call it x3, whose tangent line is parallel to the pink line. By the main value theorem, there is a point x3 between x1 and x2 such that the derivative, right, cosine prime, I mean, we can call this, let's call y equals f of, let's call f of x cosine of x. So f prime at x3 equals this slope. Is that making sense? Now, what's the derivative of cosine? Negative sign. So this would be, the left-hand side would be minus or negative sign of x3. So what this is saying is that negative sign of x3 is cosine of x2 minus cosine of x1 divided by x2 minus x1. Okay. And now, I don't know if you remember when we were doing the squeeze theorem problems long time ago. Well, I mean a couple of weeks ago, I guess. If you remember, like the squeeze theorem problem, there was something we could say always about the value of sine or cosine. What can you say about the value of sine and cosine? Between which numbers are they? What the largest sine can be? Right, let's put it this way. One, and the smallest would be -1, right? Sine is always between -1 and 1. So minus sine is also between -1 and 1. So this quantity is between, regardless of the value for sine, for the angle, regardless of the angle, this is always between -1 and 1. So that means that cosine of x2 minus cosine of x1 divided by x2 minus x1 is between -1 and 1. And so you see, if you multiply both sides by x2 minus x1, then you get the inequality that you wanted. Is that making sense? Any questions about this? Okay, let's do another problem. And this is also another application of the mean value theorem. So here's another example. So example 3. Consider the equation 2x cubed. Let's see. Let me see which one I want to do. Okay, let's do it with something easier. Let me see if I want to do, just give me a second to check if that's the equation I want to do. Okay, yeah, let's say consider the equation 2x cubed plus x plus 1 equals 0. So let's break it into two parts. Why must this equation have at least one solution? Why can't there be more than one? Why can't there be two or three, be more than one solution? Okay, so I'll give you a chance to think about this, what the problem says first before starting to discuss it. Let me give you a second to copy it. So I don't know if you remember, the part A is actually something that we saw, I believe, for the first exam. So anyone remembers how the part A problem was solved? What would you do to show that this equation has at least one solution? Let's just find this function. What is f of 1? f of 1 gives you 4, right? Which is positive. And what is f of negative 1? That is 2, which is minus 2, which is negative. So hopefully this helps you a little bit remember what happens next, right? So you have a value where the function is positive. You have a value where the function is negative. So what could you conclude? Or what was the name of the thing that you used to say something useful? Continues. By the intermediate value theorem, it must have been 0 at one point. There must be a point between negative 1 and 1. Where the function becomes 0, which is a solution of that equation. Is that making sense? I guess part A was just to remind you how the IVT intermediate value theorem was supposed to work. So what this is saying is that we know at least for sure that there's one solution to this problem, to this equation. Okay. Now, what part B is going to ask you to show is that there cannot be more than one solution. So, like, kind of if you made a graph, I can show you here like the graph of this function. Right, if you make a graph of this function, actually kind of, it looks very plausible based on the graph. So I guess like one justification would be to, just check, like where the function is increasing, decreasing, and things like that. But there's a more like quick proof using the intermediate value theorem. So that's what we're going to try to make. So why is there only one solution? So this is what is called like a proof by contradiction. So when you prove something by contradiction, you assume that there are two solutions. So it's like I'm asking you to show that there's only one. So you want to assume the opposite of what I'm asking you to show. So you assume that there are two solutions. What does that mean? It means so that f of x1 equals 0 and f of x2 equals 0. Okay. So by the mean value theorem, there would be a point between x1 and x2. X3 between x1 and x2, where f prime of x3 equals f of x2 minus f of x1 divided by x2 minus x1. But what's the first derivative? The first derivative is 6x squared plus 1. So this would be 6x3 squared plus 1. That's what the first derivative gives you evaluated at this point. And what's the right hand side? What's the numerator? Well, by assumption, each of these is 0. So you get 0 over x2 minus x1. So you get 0. And is that a problem? Can anyone see a problem here? And that's impossible because the square of any number cannot be negative. Is that okay? Is that making sense? Are there any questions about this? So that's kind of like the three flavors of the mean value theorem. Like usually it's used for either like a problem that involves velocity, like a physical problem, or a problem about showing like an inequality, like the second one we did about with cosine, or like a problem showing that an equation cannot have more than a certain number of solutions, like the one that we just did. All the mean value problems, theorem problems are kind of one of those three, most basically. So like I kind of did one of each for you so that you would have an idea. They kind of feel a little bit different from the rest of the problems we have been doing so far. So it's not that in practice, it's not that difficult to identify when a mean value theorem question appears, because it just looks, like the word in it relatively different from the other ones we have been doing so far. So there's only one topic left for the exam on next Monday. I guess we can start talking about it. It's called L'Hopital's rule or L'Hopital's theorem, which is a very convenient way to find limits in terms of derivatives. So let's start talking about that. Let's take a break. It's different from what we have been doing. So let's just take a 5-minute break to clear our minds. And once we meet, I'll begin that and we'll finish it on Wednesday. But at least I'll give you the basics of it so that you have like almost everything that's going to be on the exam done today, roughly. So let's meet in 5 minutes. I'll talk about L'Hopital's result. Okay, so the last topic for this exam of next week is L'Hopital's theorem. So let me tell you about that. And again, I may not finish all of it today, but at least I'll give you like the basic formula. Okay, so this is what like people kind of become obsessed with it, like in the sense it is like a useful way to compute limits. And once you teach this formula, then everyone will just start computing limits this way, which I suppose is fine, but it's kind of like, it's kind of like this only works because we already knew how to find the values for derivatives in different using certain computations of limits. So it's kind of like it's more. You should think about it more like a way to summarize or memorize quickly certain values for limits. But it's not. It is less powerful than it seems, just because at the end of the day, it does depend on some computations we had done before. But I mean, it's still a convenient result to have. So let me just give you an idea of what it says, and then I'll write like the full details. So in L'Hopital's theorem, let's say you have a point A, and so you have like the graph of a function. Let's say you have like one function like y equals f of x, and you have another function like y equals g of x. So you have two functions f and g, and so like the idea of this theorem is that, let's say you wanted to compute. So let's say, so here's the main idea. Let's say you want to compute, you have two functions. Let's which satisfy f of a equals g of a equals 0. So you want to find you have two functions which become 0 at the same point. So there's a point A where both become 0, and you want to find the limit, right? And you want to find, is that okay? So here, to find this limit, you have to be a little bit careful, right? Because if since both become 0, both functions become 0 at a, oops, since both functions become 0 and at a, you cannot just say that this is f of a divided by g of a, right? Because that would be 0 over 0. So you cannot apply the limit there. You cannot use this. You cannot just plug in directly, right? And most limits in practice were like just like of that sort, right? So if you remember, here are some examples that fall into this category. So some examples we have done before, like for this. Well, limit when x approaches 0, sine of x over x, right? Lim when x approaches 0 of cosine of x minus 1 over x, right? If you look at these, among many others, right? Like we have a bunch of examples where if you had just like, you had a ratio between two functions, and if you just were to plug it in, you would just get 0 over 0, right? And so like you cannot just compute the limit that way, right? But L'Hopital's theorem is going to give us a way to compute that limit in terms of the values of the derivatives. So what can you do here? And again, this is kind of like the main idea. just for you to, it's kind of like I'm trying to show with the picture what's supposed to happen. So if you remember, I don't know if you remember, like imagine that you take like a point X here. Let's say you take a point X here. So what should be f of X? If you remember the approximation, right? Anyone remembers this? F of X can be approximated by f of A plus f prime of A times x minus A. Does that sound familiar? And g of x can be approximated by g of A plus g prime of A times x minus A. So we have used that in the past, right? Is that it looks does that ring a bell? So the thing is that now these are zero, right, by hypothesis. So what happens is that the limit, if you believe in this approximation, oops, I don't know what I well, what happens is that you should think that maybe you could approximate this limit as a limit as x approaches A of f prime of A times x minus A divided by g prime of A times x minus A. Okay, like that seems plausible. And if you look at this, like, well, then you could cancel this x minus A on both sides, and this no longer depends on x. So you should just get f prime of A divided by g prime of A. Is that making sense? Uh, is what I'm doing right now makes reasonable? So, and L'Hopital's theorem basically says that this is essentially correct. So L'Hopital's theorem says that you can replace the limit of these two functions with the values of the derivatives. Okay, so let me write it down. Okay, let me give you a second to copy this, and then I'll write it down like separately. So here, let me write L'Hopital's theorem. This is, give me a second, just a second, please. So again, L'Hopital's, I'm going to write for you like the baby version, like a preliminary version. I'll give you more details. So part A, or like, let's call it part one. So it says you have two functions. And this is like the 0/0 version, if you let's call it that way. 0/0 version. Okay. So what this says is that if this limit exists, then these two limits. Sorry, you have two functions, and you want to find these as assuming that the limit as x approaches a of f of x equals the limit as x approaches a of g of x, which is just 0. Right. That's the zeros. This is the 0/0 part, right? Because you can, if you were to just plug this, naively plug each, you get a 0/0. So what the L'Hopital says is that provided the limit as x approaches a of f prime of x divided by g prime of x exists, if, or let me write it instead of provided, let's write it with the word if. If this limit exists, then the two limits agree. Okay. So this actually is relatively, you see, it's not too bad to compute. So let's do some examples if that sounds good. Let's say you wanted to find the limit as x approaches 0 of sine of x over x. Okay. So we had seen the limit before. Anyone remembers what the limit was? What was the answer for this limit? So this is the form sign of, this has like the form of 0/0, right? So by L'Hopital's theorem, if you wanted to compute this limit, what you can do is instead compute the limit of the derivatives. What's the limit of the derivative of the numerator? Usually when you apply L'Hopital's, you can write something like LH here. LH here stands for L'Hopital. So what L'Hopital says is that you can replace the numerator with the derivative, and you can replace the denominator with derivative. Okay, so what's the derivative of sine? That's cosine, right? And what's the derivative of x? That's just 1. Okay, so it just gives you the limit as x approaches 0 of cosine of x, and what would that be? Yeah, it's cosine of 0, which is 1. Is that making sense? Here's another one. So let's look at this limit. What if you what does the numerator become when x approaches 1? You get 1 to the 99, which is 1, so you get 1 minus 1, which is 0, and the denominator also gives you 1 minus 1, which is 0, right? So this also has like the form 0/0. Is that making sense? So what L'Hopital says is that you can find this limit by computing the limit of the derivative. What's the limit of the numerator? What's the limit of the denominator to x? And what does that give you? What's the answer for this problem then? Yeah, so it's 99/2. And this one, like, I mean, this is for this particular case, it's a lot more easy to find the limit this way than to find it. I mean, there are other ways to find this limit, but this is definitely the most convenient one. So L'Hopital is like actually a relatively efficient way to find limits. Let me give you another one. Let's do one that involves L'Hopital twice. So let's see. Oh, let's do this one, yeah. Okay. So is that okay? Is that making sense that this is it's still 0/0, right? So if you look at L'Hopital's theorem, it says that you can compute instead the limit of the derivatives. What's the derivative of the numerator? That's just minus sine of x. What's the limit of the denominator? It is 2x, right? And I mean, here either you can compare that to the limit of sine of x over x, but in case you forgot what that was, like again, you are actually allowed to apply L'Hopital's one more time. I mean, so you can keep applying L'Hopital's. So because this is again looks like 0/0, so it still is form 0/0. So it gives you the limit as x approaches 0 of minus sine of x prime divided by 2x prime, and this is prime, and this is the limit as x approaches 0 of minus cosine of x divided by 2. Is that okay? And what's that? It's minus cosine of 0 divided by 2, so it's minus 1/2. Is that making sense? All right, so here I apply L'Hopital one more time. So I wanted to do like an example where like L'Hopital was used twice. So you are allowed to use L'Hopital one more than once, as long as it still continues to have the form 0/0. Okay. So far so good. Any questions about it? So it's like relatively, I mean, kind of useful and fun because it's just like finding limits of the you just take the derivative and compute the limit. So here's a remark. The theorem this can also be applied when the limit has a form infinity over infinity. L'Hopital's can also be applied for limits of the form infinity over infinity. So what do I mean by that? Let's try to do some examples. So I don't know if anyone remembers this limit at infinity. Do you remember how would you solve that if you didn't know L'Hopital's theorem? What was the strategy here to find this limit without L'Hopital? Anyone remembers from the first exam? Yeah, you kind of will factorize the largest power of x. So you would have factorized x squared in the numerator and x squared in the denominator to simplifications. What happens here is like if you just naively put x equals infinity, it's kind of like the numerator is becoming really, really big, right? Because you're squaring x. And the denominator is becoming really, really big because you're also squaring x. So this has like the form infinity over infinity. And so what L'Hopital's theorem says is that it's kind of the same. You can find the limit of the derivatives instead. Okay. So this gives you what's the derivative upstairs is 4x, right? And what's the derivative downstairs is 2x plus 1, right? Is that okay? So again, if you just try to plug this in, x equals infinity, like 4x just keeps growing as x approaches infinity, and the denominator keeps growing as x approaches infinity. So this still continues to have the form infinity over infinity. Is that okay? So you can apply L'Hopital's theorem one more time. And what's the derivative of 4x? It's just 4. And what's the derivative of 2x equals is that's just 2. So you just get 2. So this limit equals 2, which is kind of what we knew from before when we would pull out the highest power of x. But this is can be a little bit more mechanical, you know. So that's why it's convenient to do it this way sometimes. Is that okay? Is that making sense? For example, here's another one. Here's another example of infinity over infinity. So what happens in this case, if you remember the graph of the exponential, right? What happens with the graph of the exponential? That just keeps growing indefinitely. Okay, and we can actually draw this graph. So e to the x looks like this, and y equals x, well, looks like this, right? So both are kind of growing forever and ever. So this is also form infinity over infinity. So this limit by L'Hopital's theorem is just a limit of the derivatives. Okay, yeah, let me put it in the upper, like it is fine, but I'll put it the other way to get like an actual answer, sorry. I'll do it the other way. No, this is better. I mean, the other one would also have worked, but I prefer to get like a finite number. And so what's the derivative of x? That's just 1. And e to the x, that's like, what's the derivative of e to the x? That's just e to the x. So now you're dividing 1 by a constant that keeps getting larger and larger and larger and larger, right? By a number that keeps getting larger and larger and larger and larger. So that's 1 over like infinity, which is like 0. Is that making sense? So like if you think about it in terms of like what this means, this is saying that even though like in terms of an interpretation, this is saying that even though both graphs are going to infinity, both functions are going to infinity, the denominator is going to infinity a lot faster, which is what kind of you see here. That's what it means to have exponential growth. That's the whole point of exponential growth. The denominator, like, so e to the x grows a lot faster than x. So in this competition, the denominator is growing at such a fast rate that that carries the entire fraction to 0. that takes the entire ratio to 0, which is what you see here. Okay. Is that okay? Are there any questions about this? So there's another thing with L'Hopital's theorem that we can do, which requires us to another type of limit. So it can be used when it's 0/0 or infinity over infinity. And there are other situations in which it can be used, and the way to use it is by rewriting it so that it becomes 0/0 or infinity over infinity. That is a little bit more tricky, so it's better to just do it like from scratch once we have more time, because we don't have like enough minutes right now. So that's it. So like yeah, we just did like part 1 of L'Hopital's. There's still like part 2 left, which I'll tell you on Wednesday, and that will be the last topic for the exam. So we're almost there. So we just have to spend like at least a couple of minutes like doing like the other type of application of L'Hopital's theorem. But I think it's like a good place to end today. So yeah. So again, tomorrow we don't have classes. But I will send you as usual the summary of the class and the video in a couple of minutes if that sounds good. You too. Bye.